All right, I think we're good to go. And with that, I'll introduce the next speaker, who is Vijay. And Vijay will be talking about Onyx, which I just heard is going to be the fourth iteration of the architecture Genie. So I'm very curious to hear how that will happen and what Onyx brings to the table. And if this presentation is only half as entertaining as the Defen podcast that Vijay is also part of, I'm sure we'll have an easy way towards the coffee break. Give it up for Vijay.
Thank you. So, good afternoon. My name is Vijay. Obviously, I'm not the funny guy on the podcast, and the guy is sitting there. It's Ray. So I hope it's going to be informative at least, and a little bit of funny in that sense. So we're going to talk about data crunching with Onyx today. Before I get into the talk, I'd like to know how many of you heard about Onyx already? Okay, how many of you used it already? Okay, so that's nice. So I still have some information to give you then, I hope. This is a Clojure conference, and obviously, we need a definition. That's a running gag at the Clojure conferences now. So I looked up what crunch means. So because I named my talk data crunching. So crunch means process large amount of information or perform operations of great complexity. I really like the last phrase, especially by computer. I don't know if there are enough people to do this here already. I'm sorry. I'm too much in the podcast mode. So before we get into Onyx, I'd like to talk a bit of an overview of what do we mean by data, and then what do we have, what kind of disciplines we have in the data science or data disciplines. So I thought about it a bit, and then I divided them into 4 categories. One is data engineering, data analytics, data science, and data governance. So these are the different areas of working with data that you have these days. Maybe some of them are familiar to you already. People who are into big data, you know these things already. So what I meant by each of these parts is that data engineering is about setting up the data infrastructure, for example, extract, transform, load, or the tooling that we provide to data scientists or analytics people, and also scaling it up and dealing with the infrastructure. And it has a bit of an overlap with DevOps stuff. And then the other data discipline is data analytics, which basically means storytelling, creating dashboards, combining with business intelligence, and then giving the value out of the data. And the data science is, again, algorithms, both statistical and machine learning algorithms that your data scientists are good at. And finally, data governance, which probably most of the people don't talk about, which is about the policies around the data with the GDPR stuff that is coming up, and the compliancy and security, who gets access to the data, etc. So that is in the bigger picture. Now, what we are going to look at is Onyx. Onyx is helping you with the data engineering, because data engineering seems to be a too long word, so I shortened it to data engineering. It sounded good to me. So what do we mean by data engineering? Data engineering is sourcing and crunching and storing data. That's basically what we're doing with a large amount of data from different data sources. Now, there are a couple of challenges. Well, not a couple, but a lot of challenges depending on the size of the data, depending on the complexity, and then the type of processing that you need to do for the data. Because there are some, probably you might have heard the words like data at rest and data that is moving constantly. So you have a streaming data and you have a batch workloads. So processing them is also a fairly complex situation for most of the companies. And also these days, everybody needs data in real time. Like the talk before, they're looking for MQTT. So the real-time information coming in, you need to process and then send response to them. So there are plenty of frameworks to do this. So I think most of you have heard about these frameworks like Hadoop MapReduce, Storm, Spark, Flink, Scoop, Cascading, Cascalog, Airflow. Probably you know about some of these things already, right? So what's wrong with these things? They're not written in Clojure. That is the fundamental problem there, except for Storm. But Storm has now lost in a storm, so let's not talk about it. Okay, sorry. Well, this is an Onyx talk, so Onyx is better than Storm. That's the idea. So the real problems behind them is that they have really complex information model. For example, if you want to get into Spark, if you know Scala, it's not enough. Then you need to think about how Spark views the data. And you need to learn Spark primitives like RDDs or data sets or data frames. And then you need to understand the Spark way of looking at the working with the data, like transformations and actions, etc. And also, it's not a standard code, because the code that you write in Spark, for example, or in Hadoop, it's very framework specific. And there is a lot of difference between batch and streaming in some of these technologies. For example, Flink is stream first and then batch, because they see stream as the primary thing, and then batch is a sub case or a specialization of streaming. And Hadoop is primarily batch thing, and then Spark is micro batches. So there is a real amount of complexity around these problems. So what do we have in Clojure world then? So enter Onyx. So what will Onyx bring to you? So Onyx brings the Clojure philosophy and the thoughts around how to think about data and then how to program your systems into distributed systems programming. That's what Onyx is doing. So the definition of Onyx, or at least if you go to GitHub, or if you already, a lot of you raised your hands and you probably looked into Onyx. So Onyx is a masterless, cloud-scale, fault-tolerant, high-performance distributed computation system, which is, checks all the boxes. That's pretty much it. But this thing should be fairly evident. So how does an Onyx program look like? So an Onyx program is basically read data from the source and then transform the data into, using various steps, and finally write the data into the target. So that is the definition of an ETL pipeline. That's what you build in Onyx. But it's also not just an ETL tool, it's also a stream processing tool. So you can do some stream transformations, and then you can emit different sorts of metrics from the stream, and then you can apply Clojure functions into the stream. So next, let's take a look at the programming model. So we'll walk through what are the major concepts in Onyx, so you can build a mental model of how an Onyx program looks like. So it has a very simple programming model. First of all, you start with a workflow. In any pipeline, for example, if you are fetching data from an API, and then you transform the data, and then you connect to another data source, and then enrich the data, and then you store it into S3, or you store it into Redshift, or whatever. So that is something, general use case that for a data pipeline. And then also maybe you want to compute things like a streaming metrics, for example, over a period of time, or over event time, or over a specific session time, etc. So that's your general program going to look like. Now, how do you describe your program? In Spark or in Hadoop, in other systems, you basically write code. You write your entire program using the API provided by Spark. So you'll do some actions, you get an RDD, and then you perform actions on top of that one, and then you collect all the results, and then you store them. So basically use write using HDFS or something, some of those APIs. But Onyx brings the workflow, so if you think about the model like Spark, when you write a program, the Spark compiler will construct the distributed acyclic graph of your code. So your code is transformed into a DAG or a DAG, and then the DAG is then optimized to run on a cluster. That's what Spark is doing. Now, in Clojure, we have this fundamental philosophy of data being the center of everything. So everything should be declarative, or at least functional. So what Onyx is trying to do is bring the DAG as a top-level construct. So you start with a DAG. You define your entire processing pipeline using a data structure. For example, I'll show you a small example later. So you describe the entire workflow as a vector of vectors. So each vertex or each step in the workflow is defined as one vector, and then you combine the whole thing into the entire workflow. And each step is basically a task. So this is how, this is the simplest workflow, some input, processing something. So the input could be anything coming from Kafka, coming from any other data source, or even a core async channel, for example. And then you take the data out of it, and then you increment the value, whatever that is. It says minor transformation, and then you emit the data into something that is out. So this is how the workflow looks like. So you see the in, and then increment it connected to out. That's pretty much it. So this is how you're going to define your workflow. Now, what are these individual keywords? These are the leaf nodes, or the end of the workflow, are basically driven by plugins. Those are the things that are connected to the external systems. They can be functions as well, if you have an output node. And the middle part, the one that is connecting these parts, the transformation, is basically a simple closure function. So the increment is mapped to a small closure function that is going to get the value of the data that is coming through in channel or input, and then apply the increment function, and then emit it to the next step. So what is the data that we're dealing with? If you see other frameworks, they define their own data types, like RDDs, or in Flink, you have these streaming primitives that you have. But if you're using Hadoop, then you have these splits that you use, input split that you deal with. So Onyx calls it a segment, but segment is basically just a closure map. So there is nothing magic around in that one. So you take maps, and then you keep transforming the maps until you want until whatever the output that you want to have, and then you emit that map finally. So that is the data that is flowing through the graph. So in this case, for example, the data that is coming through from the input channel or the input could be just a map of having a keyword count and then 1, and then you extract the count value, update in or associate, whatever that you want to do, just map functionalities, map functions, and then just emit the value out. Now, the increment itself is called a task, and that is the unit of work in Onyx. So it could be an input, it could be a processing step, or it could be output. So the input and output, as we discussed, are connected to the plugins, and the processing step is driven by functions. Now, we define the workflow as a series of steps using your DAG, and then now we map those keywords into something. That is the catalog. That's where you are getting the values of different steps or tasks. So this is how a catalog looks like. So this is again the catalog for the workflow that we discussed already. So you see the keywords, the in and increment and out. So those are the ones that are connected in the workflow. So you define your catalog with different tasks, and each task has some specific properties specified via keywords, and you can also parameterize them by adding more. For example, if you want to have the function in the middle is not increment, but add some other integer. So that integer, then your function is going to be just an add function, and then you can pass a parameter. So you can use the same instance of the function as multiple things. So add 7 or multiply by 3, whatever, that kind of stuff. Now, in this case, the plugins are basically co-racing plugins. So the data is coming through the channel of co-racing channel called input, and the data is being read or fed into the next task, which is increment. That is a plain closure function, and then the data is emitted to, again, a co-racing channel that is output. Now, there are plenty of plugins written for Onyx. Right now, we have co-racing, which is more like for your testing, for making sure that you are to run locally, that kind of stuff. So because you don't need an external system for that one. And then you have Datomic. So Onyx can connect to Datomic plugins, both input and output. And some of these plugins, HTTP, as far as I know, is only output plugin. So you can call an HTTP service as an output with the JSON payload. The one that you're emitting, the map will be sent to HTTP. And you can also read from S3 and write to S3, Elasticsearch, Redis, and Kafka. So with these plugins, you can use Onyx as an ETL pipeline. So that means you can build your own ETL pipeline using Onyx that is going to shuffle data from one medium to the other. For example, if you have a lot of data in Elasticsearch and you want to ship it into Kafka, and then from Kafka to somewhere else, then somewhere else being one of these plugins, then you can easily do it with Onyx. So just connect the plugins and then write the functions that you need if you need any transformations. If you don't need any transformations, then it's just going to be identity over that one. So the workflow can be, obviously, if you see this workflow, this is looks very simple, but you can have very complex workflows. So one of the examples I picked up from the from Learn Onyx workshop thing. So this is the DAG. So as you can see, it has 3 starting points actually from the DAG. So A, B, and C are the initial nodes where you get the data from, and then it branches out at D. So you can also create this kind of complex graphs in your Onyx workflow. So if you transform this into vector of vectors, which is basically the workflow data structure, it would look like this. So it's A connected to D and B and D, etc. So one of the advantages is that because it is completely data, that means you can generate it from any other tool because it's just Eden, right? You have this vector of vectors. So you can create a front-end tool, you can create some other language that is generating this workflow for you. and you can manage it externally to the system. So if you compare this to other systems like Spark, for example, it's driven by API. That means you cannot see the DAG separately. You cannot separate them out. So you can manage workflow out of the system and then build it using external tool and then push it into Onyx. That's the advantage we have. That's the separation of things. Now, of course, when you have this complex branching, obviously you want to think about, okay, maybe there must be some sort of a control on whether I want to switch to this branch or not. So you want some sort of a condition around it. So for that, Onyx provides something like a flow conditions. So that is basically, again, closure functions. Everywhere is just closure functions. So there is nothing magical API running inside Onyx. So that's what it sets apart itself from other distributed computation systems. So predicates, they control the data flow direction. And essentially, you emit a Boolean to say whether I want to go to the next step or not. So even this one is described using data, again, a data structure. So you have a flow from the input stream and then to multiple places, whether I want to go to the next step or not, is driven by a closure function, which is called even or zero. So only you want to send some data only when I have enough clicks on this ad, for example. If you're getting ad data and you think about only I want to calculate something if the clicks are more than 17 or whatever. So you can add flow conditions. And then based on that one, this segment will flow through the workflow, depending on this condition being true or false. And the other issue that you might think about is, during these steps, you might need some external resources. For example, I'm getting the data from S3, which is stored by somebody else, I don't care, some CSV file, and I'm reading it. And while I'm reading it, that might be an external data source, and then now I need to connect to another data source like a database, and then I want to enrich the data by connecting to the data source that I have during my processing, and then emit the final value. So for those things, that means during the execution of the task, you want to plug into this lifecycle. So Onyx gives you a way to plug into these lifecycles some stateful values or even changing the behavior of the task that you're executing. So we have a lot of hooks in the task execution in Onyx. For example, you can put in whether to start a task or not. And before the task starts, you can enrich the segment map with additional values, like a DB connection, for example, or something else, or some configuration parameter. So you can introduce these things within the lifecycle. So then you use that value to enrich your workflow and then emit appropriately. So there are multiple stages where you can hook in. And these are also really good for one of the use cases for this one, probably better explained by Michael, is that you can have logging external to your program, because you can just write this logging, all the events that you're getting in. If you want to log to another system, you can hook into the lifecycle. So you don't need to specifically write logging code within your functions. And also you can collect metrics without even writing them into your functions that are actually doing the transformations. So you use the metrics. For example, how many events I've been processing between these two steps. You can just add the metrics code using the lifecycle plugins rather than writing your own code within the functions. So you make functions really pure in a sense that they're only operating on segments. And then rest of the stuff is plugging in. You're going to plug in using lifecycle things. Now, when I started the talk, I said Onyx is not just for the batch processing, but also stream processing. So there are some streaming primitives. Onyx provides the streaming primitives using something called windows. So windows are essentially the fundamental difference between batch and stream is that batch, you know that it is going to be some sort of a bounded data. So you know there are going to be 20 files. I'm going to read each file, process it, and I'm done. And then it'll be triggered or managed by external system, probably something like Oozie or some other system like Airflow that is going to trigger. Or maybe if you are, much more Unix guy, then you tend to use cron job every now and then to trigger another batch processing of the data that you're getting. But stream is more about it is going to work on possible infinite amount of data. So the data is going to stream in from different systems, and then you don't know when it is going to end. But then you want to have some sort of a processable boundary within the stream. So that's where the windows concept comes in. So you define a window and you connect it to a task, and then you say, okay, for this window, I can have a fixed window, which is basically going to go through the whole thing as a fixed step-by-step thing. Or you can have a global window, which is going to be like all the events together. So every segment that is coming in, you can have a global window. And you have a sliding window, which basically slides through the thing. These are fairly similar to Google Dataflow, if you're familiar with Google Dataflow related things. Now you collected the data for a window, but now you want to do something with the data. I mean, you can't keep collecting the data constantly. So windows are only defining that I have collected some data for within the window, but then you need to do something with the data. And that is done by triggers. So you define a trigger for a given window. So if I collected around, 200 events based on my fixed window size, now I want to aggregate them and then do something with the data and then release the data. So this is where you can decide to just drop the data off, or you can also decide, okay, every 3 seconds I want to push the data into some other system based on the window size or how window data is going to be saved. So in this example, it's basically the same window that we have before, which is the collect segments. And then this is trigger, and we have different types of triggers here as well. So there could be a timer trigger, so every certain amount of time you trigger a trigger, okay? And then you collect the data, and then from the window, and then do something with the data. So here we are writing it to write to DynamoDB. This is the example that we have in the documentation as well. So you can write the state every 5 seconds from the window, actually. And then you can also discard the state because you're not actually going to keep the data, so you're going to empty it out. So so we have workflow, which defines your data pipeline. You have a catalog that is going to provide the tasks that are executed, which are defined in your workflow. And then you have life cycles to plug into your tasks. And then you have a window abstraction that is going to track the data in the unbounded stream of events. And then you have triggers that are going to trigger based on the collected data in the window. Now, how are we going to combine all these things together? So all these things together, what Onyx calls is a job. So you define a job, which is basically one workflow with the given catalog and given life cycle and some sort of a flow conditions, whether to switch to a specific branch or not, whether to execute something or not. And finally, the task scheduler, because these jobs are going to execute each of these tasks you specified in your pipeline. And you can also specify what kind of scheduling that needs to be used. So there are different types of schedulers. Right now, it's a balance scheduler. That means you have multiple peers that are going to run these tasks. So far, we only defined or declared what we want, but we don't know where this is going to be run. So that is where the peers come in. So the peers are the things that execute the tasks. So you're going to submit the job to one peer. But remember the first word in the definition of Onyx, it's a masterless system. That means like Spark, you submit your job to a driver in Spark. But in Onyx, you have everything as a peer. So you submit your job to a peer, and then the peer is going to pick up the job, and the state is managed in Zookeeper. So the Zookeeper is going to manage the job state between different peers. And when a new peer joins, it's going to ask Zookeeper, are there any tasks for me to do? And then it's going to execute that one. And then you deploy your job into different peers. So there is no one system that is going to, or one entry point to your cluster. This is something it took for some time for me to figure out, especially because I'm coming from Spark, and Spark has this driver notion. So you submit to driver, and then it is running on Yarn. It's running on Spark cluster. And then there is something that is already running that I submit my jobs to. But Onyx takes the different route because to give more flexibility to you, so you can run your job on any machines. All you need is just any VM or a container, and then submit your Uber jar to run on that machine. And each of these peers will have a configuration that says which Zookeeper instance to connect to. So all these peers which are connecting to the same Zookeeper instance, they form a cluster, so to speak. And then they're just going to pick the jobs from Zookeeper and then execute them. Your workflow is executed on those things. So the next question is, okay, I made my fancy data flow and workflow, and then I implemented all my closure functions. I tested them. Everything is done. Now, how am I going to deploy these things? So to deploy these things, as I said, you just compile Uber jars and then put it into Docker images, and then just start multiple Docker images with the same configuration. That's it. And then they talk to each other, and then they find each other to grab the job information from Zookeeper and then execute them. So it's a fairly different model compared to the other system that you're used to, because usually if you go for other distributed systems, you need to install the software or install Spark client on multiple machines or Flink client on multiple machines. This is a bit the other way around, because it's a self-contained Onyx program that can communicate with other peers and then get the information it needs, execute it, and then return the data back to specific nodes. So, in summary, what is Onyx going to give you? The Onyx is going to bring the closure philosophy of simplicity to distributed computing. So you don't need to learn additional API. You don't need to learn a different programming model. It's all driven by the closure way of looking at data being data, and then use data to use Eden to specify your constructs of your distributed programming. And Onyx is a data-driven distributed programming model and also execution runtime, because you're bundling Onyx jar. So there is also execution runtime. So it's basically two parts. And it is simple to construct and reason about. This is something probably difficult to explain unless you write enough Spark programs and then start writing something similar to Onyx. Because now you're not writing any Spark programs, but you're writing plain closure functions and then combining them using Onyx's API. Not even an API, but Onyx data structure or the data model. And finally, it's also a hybrid batch and stream processing model. So that means you can do batch for the work as, if you want to process like a lot of batch loads, you can do that. Or if you want to do streaming primitives or streaming stream processing, you can do that with the same code base. So all you need to define windows in such a way that you can process the data. So where to go from here? So you can check out onyxplatform.org. Probably you know this already. And there is also Gitter thing that most of the Onyx developers hang out. And there is also an excellent tutorial called Learn Onyx that you should really, really play with. It's a really simple step-by-step thing. You get to play with all the concepts in Onyx as in a test-driven way. So I would really recommend that. So that's pretty much it from me. So my name is Vijay, and I work for WorkSpot in Amsterdam as a lead data engineer, setting up the data team there. And I'm also co-organizer for Closure Days. This is a complementary conference to ClojureD. And we'll be there on 21st April. It's a free conference. Tickets are almost gone, actually. So please rush if you want to get a spot, or just talk to me. I can arrange something for you. This is going to happen on April 21st, and the CFP is still open. So if you want to talk there, please talk to me or submit your CFP. And of course, I'm also part of the other thing that you probably know, and the Clojure podcast that we're doing. So that's pretty much it. I think we still have 2 minutes for questions.
Thank you.
Short question regarding batch processing. Is there any notion of scheduling mechanisms in Onyx, like some internal cron or something that simplifies the life for, I don't know, doing some daily routines, for example?
As far as I know, no. Because within Onyx itself, there is nothing like a quad scheduler or something. So you probably want to trigger it from external system. So you will end up using cron. So.
Hi. Oh.
Hi.
Sorry. How do you do fault tolerance? I know that in other stream processing frameworks, there's this concept of rolling snapshots and doing that regularly. And if something fails, you can roll that out again. Do you do that similarly, or what's your concept there?
Okay, that's probably the internals of Onyx that I'm not really that familiar with, but depending on the discussions I have so far, so Onyx maintains like a log of the events that are happening. So it keeps the every step in the workflow, every peer contributes to the log. So technically, it should be able to, if a peer goes down, it should be able to pick it up from there. So I'm not really that familiar with the whole thing. But maybe what you're referring to is something like Flink's snapshot mechanism, right? Yeah, but this one uses basically a log. to store every operation that happened to a segment. Yeah.
You said near the end that it's a very simple system to write for and to reason about.
Yeah.
And I mean this like totally non-snarky, but is it also an easy system to reason about? Because I tried 2 or 3 times to get started with Onyx, and I basically always just chucked it out the window and just wrote pure functions in the end, because you end up writing this huge DAG. The learn Onyx thing is not particularly well geared up for like a beginner into the system, but I'm willing to bet that the ramp up cost may be worth it when you get there. But is it not that you're kind of maintaining this whole DAG in a way that you wouldn't have to think about if you were reasoning about a normal closure pure function system?
Yeah. No, that's a good point. The thing is, the question sounds similar to me, like, should I switch to Cassandra versus MySQLite? I mean, it depends on your scale. It depends on what level you're trying to do. So this is not built for like, okay, I have a small DAG. Like, for example, input and increment and output. I mean, that's a thread macro. I mean, why the hell would I even use Onyx for that? That doesn't make any sense. But the advantage that you get is when you need distributed level of processing. So if you have that amount of data, if you have that amount of workload that one machine cannot tolerate or one machine is not sufficient, then you think about this step. I'm pretty sure, probably the meme like, it's not big data if it is fitting in the memory. And then you can write a normal closure program and get away with using channels or using atoms, or just normal closure primitives should be enough, depending on the size. But this is for larger amount of data that you want to process. On the other side of it, as I said, I don't see it just like a DAG execution engine, but I'm thinking more like a stream processing. So that is not possible in normal programs that easily. So that's how I see it. It's a scale. Yeah.
Okay, maybe we have... How many more questions do we have?
Okay.
Okay, let's do 2.
Yeah, I'll be at the coffee break, so please come and poke more questions.
Okay, Zookeeper?
Yeah.
Is that necessary?
Well, it's kind of a necessary evil in all the systems these days, because there is no other distributed state management system these days. So that's why Kafka uses it. But Kafka people are slowly bringing in the stuff that you store in Zookeeper into Kafka itself. For example, I think it's the checkpointing used to be in Zookeeper, and now it's moved into Kafka. That is a question I think I post on Gitter channel and then ask Mike. I'm not really like Onyx developer. Sorry. But that's a good one, though.
Hi, great talk. One question I had, which basically, how do you do data locality?
Data locality.
Yeah.
So the data itself is flowing through the network already. So it's not similar to Spark in that sense that it is going to load the data into memory, but you are sending the data through because the communication between all these peers is happening with Eron. So if you are processing the data from the plugin, that is the entry point. So that's where you're reading the data from. So it's not really comparable to, if I understand you correctly, data locality is like you're running a big Hadoop cluster and then you put processing loads on the cluster, and then they're going to go to the appropriate data node, right? I don't think it's a similar model here. It doesn't apply here because the data in flight is always in the memory, going through the network and then going through that one. Yeah.
All right, awesome. So I think we have to end the questions here. The coffee break started 2 minutes ago. It's for half an hour. And let's give Vijay one more round of applause and enjoy the coffee break.